Hi guys, hope you're all doing well. New start to a new topic. A few minutes just thinking about the big themes we're going to look at, and then into the notes. So first up, in this topic we'll be answering the question, how can we apply calculus to motion in one dimension? So we'll be taking the work that we've done already in calculus with our differentiation or integration, and we'll be putting that in a practical context. So the first thing I want you to think about really are the related questions below on the screen there. Like, what is motion? How does it actually work? What are the relevant quantities that we're concerned with? And how do those ideas rely on calculus? And to get you thinking about that, I've included a link to just a really quick 4-minute video all about a paradox you might have heard before, Zeno's paradox. So what I'd like you to do is pause this video now and watch the TED video if you haven't already done so. So if you watch the TED video, the Zeno's paradox, as I'm sure you understand, comes down to the idea of a sum of an infinite number of things giving you a finite quantity. And really, to understand what's going on here, we have to use the themes of calculus and to use this idea of a infinite number of infinitesimally small things to define velocity and acceleration at in an instant, in an infinitely small moment. And Zeno's paradox really gets to the idea of that, and why we need that idea of infinitely small quantities to be able to make sense of what we're doing here. So in today's video, we're not actually going to get onto the calculus aspect so much, but we are going to consider just the concepts of distance, speed, and acceleration, scalars and vectors, and we're going to look at how we consider rates of change. So first thing I want you to think about is this problem with Mr. O'Sullivan. So take a moment. Mr. O'Sullivan's running 5 kilometers in a straight line from his house, and then he turns around and runs home exactly the same way. And overall that takes him 45 minutes. What I want you to think about is, what is his average speed and what is his average velocity? You should have numerical answers for both of those. I'll give you 10 seconds to have a think. Pause the video if you need to. Try and come up with your answers. Okay, so the key thing here is the difference between average speed and average velocity. And we'll get into this in a little bit more detail. But for the average velocity, well, that's quite simple, because the average velocity just cares about where Mr. O'Sullivan starts and where he finishes. And so his average velocity in this case, because he gets back home, is always going to be 0. So if I just switch over and show you on paper here what's happening, and we're going to use these kind of diagrams to consider motion today, is if Mr. O'Sullivan's starting at his house, he is running along a number line until he gets 5 kilometers away, and then he is turning back and running home. So this is his run. This is the kind of chart we're going to use when we think about this motion. He starts off at home at t equals 0, and overall it takes him 45 minutes, so 3/4 of an hour, to get back to where he started. So the average velocity, that concept, we'll talk about this more, that is independent of what happens in between. We just care about what happens at the beginning and what happens at the end. And so what we look at is the change in position. And the change in position is 0. He hasn't moved, but the time has gone on by 45 minutes, but that doesn't impact the average velocity the average velocity is 0 meters per second. Average speed is different though, because the average speed takes into account not the change in position, but the distance travelled. And so the distance travelled over this period is 10 kilometers per hour, and then the time that has elapsed is 3/4 of an hour. So it's 10 divided by 3/4, so it is 40/3 meters per second, or in other words, 13.3 meters per second. So we've heard these words velocity and speed and average before, but we just need to be a little bit careful and precise in our definitions. So let's get into the notes. We'll put some of the content in there, and you should be able to try the questions yourselves. So first up, maybe a bit of new vocabulary. In these kind of questions, we're talking about one dimension. So we're imagining Mr. O'Sullivan running up and down his number line. And in that case, our formal definition of that kind of motion is rectilinear motion. We're just moving up and down a number line. So when we do this, a couple of basic assumptions. We're going to model all objects as particles. And what that means is when we bring into play forces that create acceleration, we can consider that all forces act through a single point on our object. And what that means is there's going to be no spinning. So we assume that any object or anything that is moving, in this case Mr. O'Sullivan, he's just a particle. Any forces that act on him must be going through a certain point. Is a simplification, an assumption that makes our modelling much easier. Then in all the questions we're doing, we've got to be clear about what's a scalar and what's a vector. So thinking about scalars first, they only have magnitude. We're not interested in their direction. Things like distance travelled. Distance is a scalar, speed is a scalar, and for acceleration we don't really have a different word for it, but sometimes we'll use the phrase magnitude of acceleration. And then the final thing that is a scalar that we often use is time. In terms of vectors, well, the equivalent for distance travelled, we could have position, which is relative to the starting point or an origin. So we can consider a position to the right to be positive, a position to the left to be negative. And then we can also consider displacement. That's a different concept we'll come on to in a minute. The equivalent of speed is obviously velocity. And if we're not interested in the magnitude of acceleration, but just the acceleration itself, well, that has a direction. That can be positive and negative, and those things are different. So we're going to work through these kind of categories one by one. First thing let's consider is position, displacement, and distance. So when doing rectilinear motion, the position of a particle in one dimension is the signed distance from the origin. So right is positive. Anything to the right of the origin, positive. Anything to the left, negative. The displacement between 2 points in time is the net or overall change in position in that time interval. So you just consider where you started from, where you finished, and you consider then the change in position between those two times. Whereas the final one, distance from the origin and distance travelled, well, those are scalar quantities. They will not have a sign. It doesn't matter which direction you're travelling in. The distance you travel doesn't change. Okay, so enough of Mr. O'Sullivan. We're now on to James. James is moving up and down his number line. What I'd like you to do is pause the video and see if you can apply these concepts to this non-calculator example. Give yourself a few minutes, then restart the video, and I'll go through it. Okay, so if you've had a go at this problem, we'll go through it bit by bit. Initial position, so initial is when t equals 0, so we just substitute t equals 0 and we get x equals 6. What does that mean? That means that James's initial position is 6 centimeters to the right of the origin. So starting 6 centimeters to the right. Then as for his displacement at t equals 8. So the first thing we do is we find the position at t equals 8. So we substitute in and we get 64 minus 56 plus 6. So that's 70 minus 56, so that's 14. So his position, so position is 14 centimeters to the right. So the displacement is 14 minus 6, so it's 8 centimeters is the displacement. And that's in the positive direction because it's moved from left to right. For part C, now it starts to get a little bit interesting, and this is where our number line becomes useful, because we have to consider the overall journey. So what have we found out so far? Well, we found out if I've got an origin here, then James starts off at 6 centimeters to the right, and he ends up at 14 centimeters to the right. We don't really know what happens in between, and so we don't have an answer yet about distance traveled. So what do we think about? Well, I'm going to think, well, when does the velocity ever equal 0? Do we ever have a stationary point? So I'm going to differentiate this expression, and that will tell me that the velocity is 2t minus 7, which tells me that when the velocity equals 0, we have a stationary point. Quite literally, James is stationary when t equals 3.5. So let's think about, well, what is his position when t equals 3.5? We substitute that back into the original. So that's 3.5 squared minus 7 times 3.5 plus 6. And that comes out as minus 6.25 centimeters. So if I put that on my number line, what's happening here? Well, I'm starting at point 6, but my initial velocity, if I look at this, is going to be negative. So I'm traveling towards the left, I have a stationary point at minus 6.25, and then I travel back to the right and to that position of 14. So to represent the motion, must look like this. Just watch how I draw these diagrams. I have my times, t equals 0, t equals 8, and t equals 3.5 for the turning point. The question is, what is the distance travelled? Well, I've gone from 6 to minus 6.5, so that's 12.25, and then I've gone from minus 6.5 to 14, so that's plus 20.25. So overall, I've travelled 33 meters, and that's my solution. So, yeah, notice the little diagram, really helpful, really clear in helping us work out distance travelled. Okay, let's flip it over, and let's talk a little bit more explicitly about speed and velocity. We talked about it just a little bit then. So, some definitions. A particle's average velocity is defined as the change in position divided by the change in time. So you work out where it is at the start, you work out where it is at the end, and you look at the difference between them. The velocity, though, when it's not an average, is the instantaneous rate of change of position with respect to time. And to figure that out, well, we have to use our calculus, we have to differentiate, because we're talking about an instant, a moment, an infinitesimally small period of time. Just in terms of notation, maybe to introduce something a little bit new, velocity is dx by dt, so the derivative of x with respect to time, which I can also write as x dot. And that's x dot instead of x dash. X dash is the derivative of x, whereas if we're differentiating with respect to time, we have a special little notation for that, which is a dot above, that tells us that that is dx by dt, where t is time. So we'll use x dot as we move through this chapter. What is speed? Well, speed is the magnitude of velocity. It's just independent of direction. And then, similar to the example we looked at right at the beginning, average speed takes into account the distance travelled over the change in time. And your big note here, and this is important, average speed is not the same, or not always the same, cannot be assumed to be the same as the magnitude of average velocity. And this is kind of a common mistake that people make at the beginning or when they're under pressure. So something worth remembering. You can't just take the magnitude of average velocity to work out average speed. Let's have a look about why. Same example as the previous page, still talking about James on his number line. Have a go at answering these questions. Pause the video. Start it again when you're done. Okay, so getting into this question, James's average velocity in the first 8 seconds. Well, average velocity just takes into account the change in position. So average velocity would be the change in position. Well, he finished up at 14 centimeters to the right and he started at 6. He had this displacement of 8, and that happened in 8 seconds. So the average velocity is 1 meter per second. But if we think about the average speed takes into account the distance that he's travelled. He's travelled 33 centimeters in 8 seconds, so that is 4.125 meters per second. Notice both are positive, but the average speed has a greater magnitude because it takes into account the movement in both directions. Well, why are these different? How do we understand that? The simplest thing I want you to take away is that average velocity only takes into account the net change in position, so the beginning and the end. It doesn't care what happens in between. So average velocity is just where did you start and where did you finish? But average speed considers the journey in between. And obviously both of those concepts are logical, they make sense, but they just give us slightly different results. Then let's look at part D. Part D says find his max speed in the first 8 seconds and the time in which that occurs. So when we're looking at maximums and minimums, what we're always thinking is that could happen at a stationary point or it could happen at an end point. So the first thing I'm going to consider is I'm going to consider stat points. From my previous work, I had that velocity equals 2t minus 7. So dv by dt, the acceleration, is just 2, which is never equal to 0. So there are no stationary points for the velocity. So you're not going to have a maximum velocity in between the endpoints, which means to work out where the maximum speed does occur, we just need to consider both endpoints. So now I'm going to consider those. First one is t equals 0. At t equals 0, the velocity is minus 7 meters per second. So the speed is the magnitude of that, which is 7 meters per second. I think it's centimeters per second, isn't it, in this example? The second endpoint for the motion is t equals 8. At that point, the velocity is 16 minus 7, so 9 centimeters per second, which is greater. So the max speed is 9 centimeters per second, occurring at t equals 8. In terms of your rigor there, guys, it's just really important. If you're looking for maximums in motion, you consider every time the endpoints and the stationary points to figure it out. Then, final little note at the bottom of this page before we just talk about acceleration. It's pretty common to move between kilometers per hour and meters per second. So when we do that, 1 kilometer is the same as 1,000 meters, and 1 hour is the same as 60 minutes, which is the same as 3,600 seconds. So if I convert both, what I end up with is 1,000 over 3,600 meters per second, which simplifies to 5 over 18 meters per second. And that's really the result which you just might want to refer to in your logbook. Going the other way, you do the reciprocal. So 1 meter per second is 18 over 5 kilometers per hour. And just giving this to you now so that you don't have to do it from scratch. You have that note in your logbooks for your paper 2 exam. Okay, one more page. So we're just talking about acceleration and magnitude of acceleration now. The particle's average acceleration in a given time interval is the change in velocity divided by the change in time. And just as we did with velocity, what are we doing when we define acceleration? Well, it's the instantaneous rate of change of velocity with respect to time. And so it relies upon an understanding of infinitesimals, moments, tiny, impossibly small intervals of time, and that's why it depends on calculus. Our acceleration, well, that's dv by dt, so it's the second derivative of x with respect to t, and using this dot notation, it's x double dot, second derivative. In terms of our language, well, if the velocity and acceleration have the same sign, that means that the magnitude of velocity, the speed, is increasing, so we say that that particle is accelerating. If the velocity and acceleration have opposite signs, well, then the speed is going to be decreasing, and so we say that is decelerating. And then the one which we always need to recall, if a particle's acceleration is 0, well then yes, it might be stationary, or it is moving at a constant speed or constant velocity. Good stuff. All right. If you're feeling pretty good about these concepts, give yourselves a few minutes. Moved on from James to Ollie now. Ollie has a new equation for his position. First thing, just try and sketch 3 different graphs for position, velocity, and acceleration, and then answer the questions beneath. Best of luck. Okay, I'm going to show you my solutions now, which I just did a little bit earlier. So, first thing I did as I was thinking about the first sketches is I quickly differentiated twice. So I started off with my equation for position, then I've got my equation for velocity, which is minus 8t plus 8, and then I've got my equation for acceleration, which is minus 8. And then I would normally work backwards if doing the sketches. So a sketch of acceleration, well, it's constant at a value of minus 8. If I then look at the velocity, well, the velocity is decreasing, y-intercept of 8, gradient of 8, x-intercept of t equals 1, meaning that as I move back through these, I obviously have a quadratic, have a negative quadratic. It starts off with a value of x equals 12, is my y-intercept. Then if I think about my maximum point, well, the maximum point is going to occur when the velocity is 0, so velocity is 1. I substitute that in, and I get 16. So I have my maximum displacement at 16. And then the remaining thing to do is just find this x-intercept. If I factorize, I get that the equation here is equivalent to minus 4 times t minus 3 times t plus 1. So this intercept must occur when t equals 3. So if I've got my sketches, the next part of the question says find the time at which its velocity is 0, represent the journey on the number line, and this is the kind of sketch which you need to complete. Notice I've got my displacement along the bottom, and I also have the times that go with those different displacements. So we're starting off at 12, we go up to a position of 16, then we spin around, and we know we hit 0 when t equals 3. In terms of part C, a little bit of language that's maybe unfamiliar. It says in the third second. Well, if you think about this a little bit, the first second goes from t equals 0 to t equals 1. The second second goes from t equals 1 to t equals 2, which means the third second must stretch from t equals 2 to t equals 3. And so to work out that displacement, I need to substitute in to work out the positions at those 2 points. When t equals 2, x equals 12. When t equals 3, x equals 0. So the displacement is minus 12 in that third second. And then the final question is for the distance travelled and average velocity. Distance travelled using my number line is 4 plus 16, so that's 20 meters per second. And then the average velocity doesn't care about distance travelled, it's just the change in displacement. We go from 12 to 0, so overall we're moving towards the left. Excuse me, an average velocity of minus 4 meters per second. Okay, good job on this today, guys. I'm going to there's one check-in multiple choice question for you just to show that you've watched this video and that you have understood the major concepts. There's going to be 2 more videos, and obviously your homework is to complete all the associated exercise questions. Good luck. Speak to you soon.